So yeah, Pradeep, can you just confirm if my screen is visible and I'm audible or not?
You are audible, sir. Screen visible.
Okay. So, do you think people will come? Because today Ganesh
Yes, sir.
Chaturthi.
Yes, sir. Yeah, why not, sir? Let us wait for 2 3 minutes. This now getting to
Okay, okay, we'll wait for 5 more minutes. We'll start at 6:05.
right, sir. Yeah.
Okay. Yeah, so we'll start now. So
Yes, sir.
yeah, so the today's topic is incompressible viscous flow in pipes. But I mean, as the name suggests, it is incompressible case. So mostly it will be like water, liquid. Most liquids are incompressible, and some gases also certain up to certain degrees. But yeah, mostly we'll talk about liquid flows through pipes. Pipes can be of different shapes. Uh, Majority of the discussion like revolves around the circular sectional pipes, but There are some rectangular channels, some non-circular channels also. So that also you can keep in mind. And viscous. So that means today we are considering the viscosity effects of the fluid that is flowing through the pipe. And and we have talked about this Reynolds number in some of the previous classes. So Reynolds number essentially, uh, it is the criterion that is used to uh, distinguish between two cases of viscous pipe flows. One is called as laminar flow and another one is called as turbulent flow. We have talked about these categories in past also, but here maybe today we'll do some further, like one of the aspect we'll further explore. So yeah, so we'll start. So first there are some important concepts that you should know. Uh, like before going to any this thing, so there is, like if you see, uh, let's say Reynolds number formula, if you see, it is rho, the mean velocity. We'll use the superscript of horizontal line on velocity to represent it as a mean, or maybe we'll just skip it because in this chapter mostly we'll use mean velocity. Wherever it is not, I'll tell you. So, and there, then there you have this diameter term, which is d, which is actually not a diameter, it is a length scale. But for pipe flows, the important length is the diameter, so that's why we consider it d. And the viscosity of the fluid is mu at the denominator. But as I said, there are different configurations or cross-sectional pipes are available. So this is, in strict terms, it should be called as a hydraulic diameter. Some people use DH, H in the subscript also for this, but okay, we'll use D. That simplifies our life. And it is given as 4A by P. So the important thing that I wanted to tell you is A is cross sectional area of the flow. So this is the critical term. It is not pipe, and P typically we call it as wetted perimeter. Uh, Many people just mug it up and forget the difference that there is this word which is called as wetted. So what it means is like only that perimeter is considered which is in a uh, direct contact with the pipe. Uh, okay, I'll explain you what it means. Why I'm highlighting on this point is because let's say we'll take the common example of a circular pipe. For circular pipe, D, if you consider its cross-sectional area, it is, let's say, pi by 4 D square and divided by the wetted perimeter, which will be pi into D. D is the diameter of the pipe, okay? So pi gets cancelled, 4 gets cancelled, and we are left with the D. So hydraulic diameter is nothing but the actual diameter of the pipe for circular pipe. And if I tweak this condition, uh, let's say I have half filled circular pipe. So there can happen a case in which your pipe is not completely filled, it is only half filled, so it will like if you take the cross sectional view, it will look something like this, and only this part will be filled with the water. So in this case, what happens, this definition is important. The definition of A is it is the cross-sectional area of the flow. So what is the cross-sectional area of the flow? Maybe I'll use some highlighter here. So this is the cross-sectional area of the flow, and that will be equal to, let's say 4 is the constant, 4 into, instead of pi by 4 d square, it will be half of it. So half into pi by 4 d square, and then the weighted perimeter will be only this perimeter, which is in the contact with the, I'll just make it a thicker line so that people will be able to identify it. Maybe I should have used some other, 1 second. Oh, I should have properly drawn it. 1 second. Anyway, so I think this is fine. So this is your weighted perimeter, and that will be half of the pi d. So here we are saved because this half of factor cancels each other, and again we get the d. But it will not be always. I'm emphasizing on this point because there was like one time I have read about it that in some of the interview questions, this question was asked to someone who was like one of the topper of the competitive exam, and typically what happens when you prepare for any exam, you have a lot of things to remember, and then you just remember the formula for hydraulic diameter, and that is 4d by 4a by p, and therefore you forget that it's cross-sectional area of flow and weighted perimeter. So not always it is that straightforward. In circular pipe, more or less we get saved. In this case also, if I take, let's say 1/4 filled pipe, not half filled, then also I think it will change because weighted perimeter will be different and the cross-sectional area will be different. They'll not decrease or increase in the same ratio. So that is the point that I wanted to make. Let's say, and there is one important other thing also. Let's say there is a annular flow. So what happens in annular flow? The flow will be something like this, and fluid will flow through this annulus. So its ID or the inner diameter will be, let's say, di, and outer diameter will be, let's say, do. So here the hydraulic diameter comes out to be again same formula, 4 into pi by 4. Now the cross sectional area will be pi by 4 do minus di whole square divided by weighted perimeter will be pi di plus pi do. So here also you can take the pi common, and do minus di square you can, a minus b whole square formula. Oh, sorry, it's not whole square. My bad. It is each area square, and then you take the difference. So if you do that, you get it is actually the some difference of do minus di. So this is also sometimes this type of questions are asked from simple concept of hydraulic diameter. You should know. And for other things like square duct and rectangular channel, etc., if they are fully filled, you will get for square duct it will be the side, hydraulic diameter will be equal to the side, and for rectangular it is 2a by a plus b, where a and b are the sides of the rectangle. But that is same. Like use the same formula and you'll get that answer. So this is actually very neglected concept, but important one because of this half filled case. In some channel flows also this comes into picture, so therefore you should know this. Anyway, so moving on. So like we'll cover one more concept which is actually quite important. See, I've seen the classes for next week, and we have covered most of like some of those things also already in the kinematics part. So what I was thinking is I'll take this because this is very important part. Viscous pipe flow. It is, I would say, like there are like some key important topics in fluid mechanics course. One is this viscous flow.
Sir, one question. Sorry for this. You mean to say the D for circular pipe and D for half-filled circular pipe? It is same for the circular pipes basically. What is the uniqueness, sir? Because D is same, is it not?
See, it is coincidentally coming equal. This half-filled circular pipe. I just thought for ease of doing this, I'll take that. But let's say we'll take one more case. There you'll understand. Let's say we take rectangular pipe and it is fully filled. So let's say it will be something like this. And let's say this is your side A, side B, and it is completely filled. So this is your flow cross-sectional area. Here if you calculate what is your cross-sectional area, it is A into B divided by perimeter. Perimeter will be 2 into A plus B. So you will get 2AB by A plus B, right? But let's say if it is half filled rectangular pipe, so in that case, okay, 1 second. Let's say we keep the A and B same, so it will be only half filled till here, and only this much area will flow, right? So here your D will be 4 into cross-sectional area of the fluid. So it will be A by 2 into B. And if you take the wetted perimeter will be only this part. Because in this in these areas only, or on these boundaries only, the fluid is coming in contact with the pipe. So what will be that length? If you do the calculation, it will be A by 2 plus B plus A by 2, right? Because this is your A by 2 length. So if you solve this, what you get? In the numerator you get 2AB, and in the denominator you get, okay, here also it is coming A plus B. Huh? Maybe I'll take 3/4, not half, because I think in half case it is always coming same only. Let's say, but it should not, right? 1 second. Am I doing anything wrong? Cross-sectional area of the fluid flow. It is cross-sectional area is A by 2 into B, correct? There A by 2, B by 2. So 2A plus B. Okay, I'll take 3 by 4. Let's see. If it is coming same, then maybe I need to find some other examples. But it is the point that I wanted to make is you should know what area and what perimeter you are choosing. So let's say it is something like this, and it is, let's say, this depth is 3a by 4, 75%. So in that case, what will be your cross-sectional area? It will be 3a by 4 into b. And what will be your perimeter? It will be 3a by 4 plus b, because this is b, and plus 3a by 4. So now what it becomes is, the numerator becomes, one second, what did I do? The numerator becomes 3ab and the denominator becomes 3a by 2 plus b. So now you understood. This is not equal to the earlier value, right?
Yeah. Yes, sir. Yeah.
Not equal to 2a by a plus b. So when I talked about this concept, I meant that part only, because generally, like in this session also, mostly you will encounter problems in which there is a completely filled pipe. So you need not to take like much attention. You cannot. It's okay if you don't pay much attention to this concept, but like if you study fluid flow in depth, there are some flows in which you don't have completely filled pipe, and there you cannot just apply the d equal to small d or d equal to 2a by a plus b formula for the hydraulic diameter. I think if you take like half filled channel, it is coming out to be same thing only, because the perimeter and the this thing area and the perimeter are decreasing in the same ratio. But if it is not half, like this case where it is 75% filled, there you are getting different hydraulic diameters. So that was the point. Understood?
Yes, sir. Yes. Yes. Yeah.
Okay, so we'll move on. There is important this thing. So mostly like 90% of the time we deal with the circular pipe, and in circular pipe, this thing for laminar flow, in a circular pipe, this will be like most of the problems will be in this category only. So we should talk slightly more about this. So here we start with some formula, but let's say, and one more thing, when we say laminar flow, that means Reynolds number is less than or equal to 2300. This is for pipe flow, okay? For a flat plate flow, it is 1 lakh. But we are here only discussing about pipes, so we should know when your Reynolds number is less than 2300, less than or equal to, then it is a laminar flow. And the other thing that is there is there is actually a derivation to all this, but we are not going into the depth. What happens is, let's say you have a laminar flow like this. Let's say this is your center line of the pipe, and this is your radius, capital R. So therefore, like this will become your diameter from the geometry. So when the fluid flows into the pipe, when it is a laminar flow, it is observed that, and obviously there is a no slip boundary condition at the boundaries, where your velocity, let's say I'm using u symbol for velocity, is 0 on the circumference. So here it will be 0 on the both ends. This is a cross-sectional area of a circular pipe. and this u is equal to 0 because of no slip boundary condition. We have discussed about it earlier. Then there is a derivation, and from based on that derivation, what is observed is the the profile of the fluid flow that you get is a parabolic pipe. This derivation, maybe I don't know whether it is a part of this course, but when this Navier-Stokes equation is introduced and it is solved for a radial or polar coordinate system for a laminar pipe flow, you will get this velocity. This thing as you will get expression for the velocity as 1 by 4 mu. Mu is the viscosity of the fluid flowing through the pipe. It will be negative of the pressure gradient. So this fluid flow is happening because of the pressure gradient, right? So fluid always flows from higher pressure to the lower pressure. So there exists favorable pressure gradient. That means there, like between these 2 points where the fluid is flowing, here there is high pressure and here there is a relatively low pressure. So the difference between these two, delta P by, which is delta P along the length of the pipe, is the pressure gradient that you are considering here. But in terms of small elemental volume, it is typically written as del P by del X partial derivative into this thing, R square by 2 plus some constant. So this is the general equation for, one second. General equation for pipe flow, laminar circular pipe flow. And here this constant is determined by using no slip boundary conditions. So we know when your R becomes capital R, which is radius of your pipe, your velocity is 0 because of no slip boundary condition. And if you put that in the equation, let's say number 1, then equation 1 modifies as u equal to then we get C as minus 1 by 4 mu del P del X into capital R square by 2. This is straightforward algebra. And therefore your u expression is 1 by 4 mu minus del P del X into minus minus becomes plus, so it will be R square minus R square. One second. Oh, there is no 2 here, sorry. I made a mistake. It's only R square. I understand I am not giving you to the derivation of this bus, but let me, I hope it will come in the future somewhere. We will come across it. So this is your final formula for velocity. And therefore you can see if, let's say I want to find.
Sir, one question. But we equated here R is equal to R eject, no, sir. Small r is equal to big R.
Small r is like radial coordinate like this. So when you are at center, R is equal to 0. Let's say I should have written it here only. And when you are at the periphery, small r becomes capital R. So that is our sign convention.
Yeah, I got it. So yes.
Yeah. So now if you want to find maximum u, what you do? You take the derivative. Here your velocity is function of like only r, small, only one variable you have. So if you take del u by, or maybe not del u, only du by dr, and equate it to 0, you should get the r value at which velocity is maximum. So if you do that, what you get? This 1 by 4 mu constant remains same because it is a constant pressure drop flow, laminar flow. R square is the constant, so that goes to 0, so it becomes minus 2r equal to 0. So therefore r equal to 0. So therefore your maximum velocity will happen at r equal to 0, and maximum velocity will be at r equal to 0. So put r equal to 0 in equation number 2. So you get 1 by 4 mu minus del p by del x into r square. So this is your maximum velocity, and then if you take the ratio of maximum velocity, now you have to do the calculation for this is the maximum velocity that you will get at the center, and let's say you want to find out what is the average velocity across the cross-sectional area. Let's say you call it as u mean. So for that, typically what is done is you equate, let's say, u mean into the total cross-sectional area, which is pi r square, and you take an integral of your instantaneous velocity along a small circular uh, uh, infinitesimally small circular film in that area, and then what you do, you integrate u into 2 pi r dr. So this is your elemental volume, elemental area, and you integrate it from 0 to r. So basically this is your so let's say if I have a cross-sectional area of flow and there is some velocity u mean, so that will be constant across all the points. So at all small r, u mean will be same, but this small u is a function of r and it is a parabolic function as shown here. So therefore what I do, I take the integral, and that is basically equating your volume flow rate. So this is your if you want to understand that way, this is like this represents velocity into area is your volume flow rate. So this represents volume flow rate in a pipe. So you can define it in terms of mean velocity also, or also instantaneous or local velocity, that is small u. So if you do that calculation, I'm not going into that. It's a straightforward calculation, not much difficulty. You can also do it if you want. So if you do that, what you get is you get 1 by 8 mu into del p by del x into r square. And let's say you divide equation number 3 and equation number 4. From 3 and 4, we get u max is 2 times of u mean. This is very important result that you should remember, that for a circular laminar flow, your maximum velocity which happens at the center of the pipe is 2 times the average velocity throughout the cross-sectional area of the flow. Okay, so that is one thing that you should remember. And then what people do is they since I said, right, this is a parabolic equation, so to get the parabolic form of the equation, what they do, they put u max from equation 3 in equation 2, and then we get u, which is a function of r, as u max into 1 minus r square by r square. So this is also a straightforward result only. I am giving you the steps. If you want, you can follow them, and you should get the same result. Here I am not doing it because then we'll not have much time to do anything else. This is one important result. I am putting star marks wherever I think you should remember these things. And then I think you know, this uh, this average, like here I put right volume flow rate in a pipe, so it is average volume flow rate. Let's say we call it Q, and if you do that, what you get is therefore Q also we can get in terms of these things. It is U mean into pi r square, right? So what you do, you put U mean formula there, which is 1 by 8 mu into minus del p by del x into r square and pi r square as it is. So you get therefore Q equal to 1 by 8 mu minus del p by del x pi r power 4, which implies your volume average volume flow rate is proportional to the fourth power of radius. This is also important observation. See, like, don't think that I'm not solving any question, okay? Because these whatever star marks I am putting here, they are in itself questions only. If you go back and check any previous year GATE or ESE prelims papers, you will find many questions on this. I'll take some questions, then you will find out why I'm taking this. And sometimes what they do, they don't define Q in terms of radius. What they want is in terms of diameter. So we know radius is half of the diameter, right? So R is d by 2. So if you put that in this Q equation, therefore Q equation becomes like 2 to the power 4 will be 16. So 16 into 8 will be 128. So nothing changes, only this 128 mu becomes like this, and everything else remains same only. Only here pi by, okay, I'll put capital D. So pi d power 4 will come here. And again, this D is your hydraulic diameter, okay? In circular pipe, it is same to the circle diameter, but not always. So that also we discussed. So from here you have one more relation, that your average flow rate is proportional to fourth power of diameter, assuming constant viscosity and constant pressure gradient. So what people then they say is they assume that your this minus del p by del x term as del p by length. So this is your pressure drop per unit length. They assume this, and that is more or less true only for laminar pipe flow. So if you do that, what you get, then your Q becomes 128 mu into delta P by del L into pi d power 4, right? Same equation, I'm just rearranging the terms because that is how questions are formed. So if you do that, and if you take the pressure gradient per unit length term on one side, what you get is 128 mu into Q divided by pi d power 4. So this is also important result. Oh, it doesn't look good. So in some of the questions they ask this also. Maybe we'll take some questions, but you yourself can frame the question, right? Let's say typically how the questions are framed, I'm telling you. They will say there is a pipe which has an average flow rate of volume flow rate of Q, diameter D, and then what happens? Then they'll ask that when the flow rate is doubled and the diameter is half, what happens to the pressure drop per unit length? So like that, those data entry type of questions are there. We will take some of them, but before that, I just wanted to, give you all the formulas. Then there is important. So this was your pressure drop per unit length, right? So sometimes what people do is, 1 second. This is your mean, okay. Yeah, so they further modify this formula. How do they do that? From here again, you write delta P as 128 mu Q. Now L goes to that side into pi d power 4. Okay, same thing. Now what they do? They divide it by rho g on both sides. So divide by rho g on both sides. Why they are doing it? Because this delta P is in Pascal. So if you want to convert it into the head, pressure head, this they divided by delta P by rho g. And here also then again 128 mu QL, same thing, pi d power 4, 1 by rho g. This term will come. Okay. Before that, 1 second. Before that, there is one important relation. I'll do this also, but not now. Okay, I'll just cut it. So here only, what they do is next put Q equal to area into average velocity. Again, like they are going back and forth. Okay, so forgive me for that, but it is how they get some important formula and they directly use in the questions. So there you will not get the idea how this formula is there. So therefore I am giving you some derivations also wherever possible. So now if you put area is again pi d power pi d square by 4 into u mean. So what you do? You put this here. So what happens? Therefore delta P becomes 128 mu L pi d power 4, same as it is, into Q is pi d square by 4 into u mean. So pi gets cancelled, d square and d power 4 get cancelled. So therefore you get delta P of, and this 4 also gets cancelled. Here it becomes 32. Here you will have one d square remaining. So you get very important this thing, 3 mu u mean into capital L, which is the length of the pipe, divided by d square. Yeah, so this is very important formula. And note that this is valid only for circular laminar flow. This is very important to remember. I'll tell you why they do that. We'll come to that in a bit. So this is the formula. So now, yeah, and if you want to convert it into the head, let's say this is, only delta P. If you want to convert it into the head, what you do? Divide by rho g. And same, there will be additional 2 terms in the denominator. U mean into L divided by rho g d square. This is again one more formula. This is your head. And this is typically called as a piezometric head. Okay. And like this thing only is equated to the this Darcy-Weisbach equation, right? So we have Darcy Weisbach or Weisbach, I'm not sure, equation, which is the delta P by rho g, which they typically call it HF, frictional head. They give it as FL V square by 2G P. This you must have learned in this week's classes. So this F is called as Darcy's factor. L is the length of pipe. V is again your average velocity, u mean, and again 2GD, again same thing. D is the hydraulic diameter. So what they do, they equate at what equation number we are right now? 1 second. Okay, 3, 4 are there. So this will become your equation number 5, and this will become your equation number 6. So they equate them. Before going there, very important point, that this Darcy equation, which is HF equal to FL V square by 2GD, it is valid for both laminar and turbulent flow. So this is very important concept that you should not forget, because right till now we were discussing only laminar flow in a circular pipe, right? But this Darcy equation, FLV square by 2GD, it is valid for laminar and turbulent both. So don't worry about that. In laminar, we'll come to that point. Okay, I'll just do the derivation. So what they do typically, they equate FL. Okay, I'll use V now for mean velocity. 2GD equal to the 32 mu V L by rho g d square from equation 5 and 6, and we use u mean equal to V because it is easy to write. So if you do that, now many things get cancelled, and therefore what you get, LL gets cancelled. I'll use some other color, maybe some gray color. LL get cancelled. GG gets cancelled. Oh, sorry. Yeah, GG gets cancelled. 1D also goes. 1V also goes. So what is remaining is F equal to 64. This 2 and 32 become 64. Mu remains, and mu remains, nothing in the numerator. In the denominator, rho d is already there, and one V term comes here from the other side. So if you remember, this is nothing but 64 by Reynolds number. So this is very famous relationship that is very frequently used, that your Darcy factor, Darcy friction factor is 64 times divided by Reynolds number, but this is valid only for laminar flow, because this FLV square by 2GD is okay for laminar and turbulent, but this 32 mu VL by rho GD square, that expression is only for laminar. So therefore this result is only for laminar. What result? F is 64 by RE. And for turbulent flow, F is some function of Reynolds number as well as relative roughness, they call it. So this term is because in turbulence what happens, if your pipe is rough or it is smooth, then also it affects the turbulent pipe, turbulent flow regime. In laminar flow, the roughness or smoothness of pipe doesn't affect anything because your velocities or Reynolds numbers are very low. Therefore, even if you have a rough pipe, laminar flow will be okay, but it should not be very rough. I mean, there is also some other criteria there also, but let's not go there. For turbulent flow, this epsilon is surface roughness, and d is the diameter, hydraulic diameter, and epsilon by d is called as relative roughness. So in turbulent pipe flows, your Reynolds Darcy's friction factor is function of Reynolds number as well as relative roughness. And there, like one note is there. This is just a one liner. Typically, we use Moody's chart. Moody is the name of the person who studied these phenomena initially, and he gave one chart. That chart only we use to find F for laminar as well as turbulent pipe flow. So sometimes this question is also asked that what is Moody's chart? I have seen those questions, that's why I'm telling you. What else? Yeah, I think, yeah, and then there is one more thing which is, how do you say? Yeah, there is this thing called as shear stress. Shear stress, it has formula which is like this. I think it is R by 2, proportional to R by 2. Let me just confirm. Yeah, it is minus del P by del X into R by 2. This is the formula for shear stress. Therefore, at R equal to 0, if you put R equal to 0 here, what you get? Tau is equal to 0. And at R equal to capital R, which is your periphery or the surrounding or the circumference of the pipe, you get tau equal to minus del P by del X into capital R by 2. So your tau varies linearly because it is a, if you plot tau, which is a shear stress along a cross sectional area, you will get something like this. It will be linearly increasing here. Okay, so this is your R coordinate. This is your R equal to 0 line, which is center. This is your surface. So your shear stress increases linearly from center to wall, and it is maximum at tau max at R equal to R. At the interface, it is maximum shear stress. So this tau is actually tau max. And again, this del P by del X, you can replace it by delta P by L. And again, you do the same formula you can derive, okay, as we did in the velocity case. I'm not going there because it will be too much formula. And again, this is valid for laminar flow. Only laminar. That also you should remember. Apart from that, what else is there? Yeah, this circular pipe flow, it is like in some.
It is the tau max oblique. Sir, the is
No, it is. This is actually subscript. Okay, maybe that is confusing. Tau max at R equal to capital R. So this is actually that was a vertical line that represents at point. But anyway, I'll just write it as at. So now this whole exercise, this is also called as like, I mean, this is also called as Hagen-Weisulle. Maybe the spellings are wrong, but maybe you can cross. So basically, laminar plus circular pipe. And incompressible, that is the title of this chapter, incompressible flows. So that is also, I'll just put it here, but incompressible is everywhere assumed because we are discussing incompressible viscous pipe flows. So this is called as Hagen-Poiseuille flow, whatever derivations we have so far here. There is something called as plain Poiseuille flow also, where you don't consider circular pipe, you consider two very large rectangular plates, and they have very small gap in between them, and the fluid is flowing through there. So that is also one type of flow, but we are not going there because again it will take a lot of time. So yeah. One more thing before we move forward. Yeah, regarding this tau, what happens? Maybe I'll give some extra space here. Correct. Got paste it somewhere here. So typically what they do is there is something called as friction coefficient. You know, for laminar flow, there is something called as friction coefficient, which is nothing but tau wall divided by half rho v square. V is your mean velocity, and there is a derivation like what we did now, delta p by L. If you put this delta p by L value from here for a laminar flow, again you simplify that, and again this tau max is equal to tau wall, okay, because at wall only there is a maximum shear stress. It comes out to be 16 by Reynolds number. So this also one important observation is there. Sometimes what they ask is, let's say if you simplify this, so what is there? So your tau wall is 16. Now Reynolds number is rho Vd by mu, and there is one half rho V square term, right? So if you simplify, you get some formula which is 8 mu V by d. So this also is one of the important formula, because they will just give you that for a pipe, we just double the velocity and make the diameter 4 times. What happens to the wall shear stress? So if they give some problem like that, you should be able to use this formula and get the answer. Okay. So I think I have covered most of the formulas. Now maybe we can take some questions. We are already 1 hour into the lecture. Before going to that, let me just see if I have missed any formula or anything. Yeah, then there is something called as correction factors. I think there is one question in your assignment also, I think weekly assignment on this. So correction factor, can anybody tell me what is the correction factor? Pradeep, any idea?
No, sir. No. Yeah.
Okay, no issues. So what happens? See, in reality, in a laminar flow, where is it? Yeah, so in a laminar pipe flow, you have a parabolic velocity distribution. So like this, which is a function of radius. At what point of radius are you from the center? But what happens? And like in later formula, where like at all places we are using average velocity, which is u mean or capital V. So like how correct that is, that assumption, I mean, not, I should not say correct, but because of this assumption, what happens? Let's say, you know, how should I put it? 1 second. So there are, see, based on velocity, you defined momentum and the kinetic energy for the flow, right? So instead of using the actual velocity, which is parabolic in nature, if you use a constant velocity of u mean to calculate momentum or kinetic energy, there you may get incorrect values of, let's say, actual kinetic energy will be different from what you calculate using the mean velocity. Using mean velocity is good because it is easy for doing mathematical calculations, which you just saw here, a lot of them. But in reality, the actual kinetic energy or the actual linear momentum of the flow will be different. So how different is that? For that, they use something called as correction factors. So okay, maybe I'll do one derivation. I think it is also asked in your assignment also, but okay, anyway, we'll spend some 5-10 minutes. So correction factor. So one second, I'm just looking at it. 2pi RdR. Okay. So let's say we do it for kinetic energy transfer rate. Okay. So basically, it is a compensation factor because of the usage of u mean instead of actual u in calculation of parameters such as momentum, transfer rate, kinetic energy transfer rate, etc. I mean, like famously only two parameters are considered, which are like how see here it will be always rate, right? Because it is a flow, so everything is happening per second. So how the momentum, linear momentum is getting transferred, how the kinetic energy is getting transferred. So like that, you can define correction factor for other parameters also. There is no rule that says only for these two. You can define wherever velocity comes into the calculation, you can define correction factor there. So like that. So one second. Okay, so we'll do for let's say for momentum transfer rate, correction factor. Typically, it is denoted by beta. Not a rule again. Beta is just a symbol that.
It will be discussed in the class, sir, actually. Yeah.
It is done, na?
Yeah, it is done, sir. Yes, I remember. When I said beta, sir, I could get
Okay.
yes, we discussed here.
Yeah. Then thank you. We'll move on because again we would have spent some time here. One thing that you should know is that is typically not dwelled upon is for turbulent flow. Velocity distribution is logarithmic. So it's not parabolic. For turbulent flow, it is logarithmic. And what I mean by logarithmic is it is, you know, so if you have a pipe, let's say like this, and if it is the center line, and if it is a turbulent flow, if you consider this cross-sectional area, your velocity profile will look almost like this. Faster the velocity, this is your velocity distribution. Again, this is your r equal to 0, r equal to capital R, and let's say this is your flow direction. So faster the velocity, faster it will approach to the logarithmic region. Logarithmic matlab like for most of the region, your velocity will be equal to the average velocity. So basically what I'm trying to say is this part where you have, almost this part will be like almost straight line for turbulent flow. It will not be a parabolic, and therefore like at the edges you see a logarithmic variation which is very fast. Right? Log is initially log values will be increasing in a small rate, but after a point there is log value is very high increase, rapid increase. So like that. So that is one keyword. And one more thing is correction factors for turbulent flow will be larger than the correction factors for laminar flow. You can do the calculations. Oh, sorry, it is ulta. My bad. You can do the calculations and you will get the answer. Because, as I said, in turbulent flow, the flow tries to achieve the average velocity for most of the flow domain. But in laminar flow, things are very slow, relatively, and therefore it will have parabolic type of relation. So there, more correction is required in the laminar case. Less correction is required in the turbulent case. That's how you can remember. Then let's take one question which is again very famous question. For a circular laminar pipe, okay, I should not say pipe again, circular is okay. Laminar flow, at what radius your actual velocity becomes equal to mean velocity. This is also very commonly asked question. So what they are asking is, see, you have one formula for u, right? Which was, where is it? See, you have this u mean formula like this, and then you have one distribution, parabolic distribution for u. So they are asking at what small r your actual velocity becomes equal to your mean velocity. So what you can do, we can use these equations directly so that we'll not write them again. We'll just copy them. So this is your formula for actual velocity, and u mean. What is the formula for u mean? I think it is 1 by 8 mu minus del p by del x into r square. Yeah, I think it is correct. Let me just confirm once. Yeah, correct. So now the question asks, at what R these two values become equal. So let's say I give this equation star. So let's say at R equal to R prime, U becomes equal to U bin. So basically we want to find R prime. So then you just put the equations 1 by 4 mu minus del p by del x R square minus R prime square equal to U bin, which is 1 by 8 mu minus del p by del x into capital R square. So many things get cancelled. So what is this? Del p by del x gets cancelled, mu gets cancelled, this 8, only 2 remains here. So therefore R square minus R prime square or R dash square becomes R square by 2. Therefore R dash square is R square by 2. And if you take the square root, see R cannot have negative value, so only the positive root will be the correct root. And this gives you 1 by root 2 is I think 0.707 R. So if again going back to your diagram, let's say this is your pipe and I can use dash line, right, for drawing the center. I don't know why I was not doing it. So let's say this is your R equal to R equal to 0, and this is your parabolic distribution. Oi. Something like this. So what this result says is at some R dash, which is at R dash, which is 0.707 times of R, this velocity, which is, let's say, this velocity is equal to uv. This is your umax. This value. In other words, what it means that, see, similarly, here will be this, right? So this will be that R dash. So what it means is basically, so the fluid particles or the fluid flow that is happening between these two R dash values here in this region, your U is greater than U mean. Okay, and in the region which is closer to the boundaries, in this region, your U is less than average velocity. You got my point? So basically 70% of your flow is happening at faster speed than your average velocity, and 30% flow is happening at lower speed than your average velocity. That is happening because of the parabolic nature of your velocity profile. So this is important result. Now we'll take some questions because I think I have covered most of the. Yeah, then there is this head
So
loss.
this 0.0707 is standard, so it is standard for all circular features, or
Yeah, it is standard for all circular pipes in laminar region. So flow should be laminar and the pipe should be circular. Then this result is valid.
okay, sure.
Okay, so we'll take some questions. There is like there are some concepts like losses through pipes, and then there is different pipe connections together like that. We'll take them, but let's take some examples from this area only. Actually, this is very important. This thing important section of the fluid mechanics class, because most questions are asked from this only. Okay, 1 second. 75. Okay. Okay, so let's take this question. The value of friction factor F is miscalculated by 75%, not 75, 25%, and this is standard Darcy-Weisbach equation. What is the resultant what is the resultant error in flow rate calculation? So this is like, I'm telling you now framing questions will be very easy for me. I can just change one parameter and I can make new question. So okay, we'll go slowly. So here we know, and nothing is given in the problem because Darcy-Weisbach equation is valid for both laminar and turbulent flow. So there is no need to specify which type of flow it is. Head loss is frictional head loss is FL V square by 2G D. Here V is the average velocity, mean velocity, and D is the hydraulic diameter. But it is asking us that what is the error in flow rate calculation. So we are using this Q symbol, average flow rate symbol for it, right? So now we need to convert this into Q. So we know Q is nothing but AV, cross-sectional area into velocity, mean velocity. What is area? Pi by 4 D square. So therefore V is nothing but 4Q by pi D square. So you put this value here in this HF formula. Then you'll get some relation between F, HF and other things. Mainly the flow rate. So FL by 2GD remains as it is. V square will be 4Q by pi D square whole square. Therefore HF is FL. Here only I can write, no? FL 2GD into 16Q square divided by pi square d power 4. So this becomes 8 FLQ square divided by pi square G d power 5. Okay, so now we have some relationship between F and Q. So from this, what you can infer is, assuming other parameters are constant, what is the relation between F and Q? FQ square, or maybe ulta, like F is proportional to 1 by Q square. Okay. Or Q is proportional to 1 by square root of F. That is also correct, only same mathematical juggling only we are doing. This result is important for us because in question nothing else is mentioned, right? So there is no mention that the head will constant or there is no error in head measurement. So many questions will be like this only. They won't give you the complete whole picture. You need to do assumptions. So we have this result. So what they are saying is when they calculate F, they overestimated. So they, instead of calculating F as 1, they calculated F as 1.25, 25% increase. So how much is the error in calculation of Q? So let's say for correct F, flow rate is Q, and for incorrect F, it is Q dash. So from this equation, which is given by square symbol, we have so incorrect is F dash, let's say. So we can write Q by Q dash is equal to square root of F dash by F. Correct? So now your incorrect F dash was 25% more than the correct F dash. So therefore F dash is here 1.25 times of F. They have 25% error, na? Higher calculated. So what it becomes? It is becoming root of 1.25. That is Q by Q dash. Q dash is your incorrect flow rate. So that is what they are asking, right? What is Q dash? It is Q by root 1.25. Now I'll just do some calculation. 1.25 cos square root is 1.18, and if you take inverse of it, it is 0.89. 0.89 times 894 into Q. This is your incorrect flow rate, and this is your correct flow rate. I mean, when they estimated F dash, which is 25% higher than the correct value, what you are getting is, you are getting incorrect value, incorrect Q dash is, only 89.4% of actual Q. Correct? And that is what they were asking, right? Resultant, oh, they are asking error. So what is the error? Error will be 100 minus 89.4, which will be around 10 point something. Yeah, 10.6. So this is the error. So most of the questions will be like this only. Going forward, I'll tell you some questions. You will understand that. One second. There were many questions, huh? One second. Okay, take this question. This is previous year gate question. So again, it is a fully developed circular pipe flow, laminar flow. Assume the length of pipe is doubled and diameter is half. Then head loss due to friction will increase by the factor of. So this was data entry type of question, or maybe there will be options also, doesn't matter. Again, now we have this formula. HF is FL V square by 2GD, correct? So now they are saying other parameters are constant, only length is doubled and the diameter is half. Before going there, we know from this relation that HF is directly proportional to the length and inversely proportional to the D. But if you do this way, you are 100% wrong, because there is this velocity term also, right? This V square, and velocity and diameter, they are related, because your mass flow rate or volume flow rate is constant, not the velocity. So what you have to do, maybe here only you should consider V square. Now you don't know anything about velocity, but you know that like other parameters are constant, right? So we know Q is constant, which is volume flow rate. That implies with Q is equal to AV, right? And A is nothing but pi by 4 D square. Since it's a circular pipe, hydraulic diameter is diameter of the pipe. Therefore, from here we know velocity is proportional to the inverse of diameter square. You can write it is d to the power minus 2. It is simple. So therefore, your HF is proportional to the length is there. V square will be d power minus 4 divided by d. So you can further simplify it as L d power minus 5. So your head loss when your volume flow rate is constant is directly proportional to the length and inversely proportional to the fifth power of the diameter. Important observation here is HF is highly sensitive to D, and this is actually in one of our experiments also we have observed. We had one pipe of ID 12 mm in a circuit, and over the period of time it got old. After like 2-3 years, that pipe started leaking. There was some crack in between, so we wanted to change that pipe, but we could not get the exact 12 mm ID pipe. We had one spare pipe which was 10 mm ID, so we used that pipe only. We thought, what will happen? It's just 12 to 10 mm only, 2 mm dia reduction. But when we did that, the flow rate that we were getting, it was around, initially before like in 12 mm ID, it was around 8 LPM. But when you change the pipe to 10 mm, the flow almost reduced by half. So instead of 8 LPM, we were getting only 4 LPM. So like we thought it is some other problem, but after like lot of lot of thinking, we realized that, oh, if you change the pipe diameter only by this 2 mm, still the flow rate is getting affected so high. So I mean, that is why I wrote this observation here. In real practice, you should be very careful when you change the diameter of any pipe through which fluid is flowing, whether it is laminar or turbulent, because diameter is very important as compared to length or any other thing. Anyway, going forward, so again, we'll assume that our initial case is with the normal length, which is L and D, and in second case, they have told us that in the question it is told that length is double, diameter is half. So L becomes 2L and d becomes d by 2 power minus 5. So this, if you further simplify the, let's keep the numerator same. Here you have 2l into 1 by 2 to the power minus 5, which is equivalent to 2 to the power plus 5. Correct, no? Or maybe we can make our life simple. Let's not do the power calculations. Since we have same powers, we can divide them, right? So this becomes L by 2L, and the other thing becomes D by 2 power minus 5. This is simple way. So the first thing becomes 1 by 2. Second thing becomes 2 to the power minus 5. So this is 1 by 2. This is 2 to the power minus 5 will be 1 by 2 to the power 5, which will be 16 into 2, 32. This is 1 by 64. So therefore, your HF2 is nothing but 64 times your HF1. So, by doing this thing, your head loss has increased 64 times. And this 32 times it is increased because of diameter, and only 2 times it is increased because of length. So here also you can see that diameter is very critical. So this answer was 64. Let me just clarify once. It is 64. So like that questions are asked. Okay, I'll ask one direct question. This is again gate question. A fluid of viscosity 2 into 10 to the power minus 5 kg per meter second and density 1 kg per meter cube and average velocity of 1 meter per second is flowing through a rectangular duct, and the dimensions are 25 into 15 mm. Assume laminar flow. Calculate delta P pressure drop in Pascal per meter length of the duct. So this is the question. So first thing, when you see rectangular duct, first thing that should come into mind is we need to calculate the hydraulic diameter for this duct. Now here, like the convention is, they typically mention the longer dimension first, and then you can take A or B, anything you want, but that doesn't matter, right? It will be still the same only. So if you do the calculation, which is hydraulic diameter is 4A by P, and here it is completely filled up, so there is no partial filled or anything, so normal thing. So it will be 2AB divided by A plus B. You can put A and B as 25 and 15 mm, and if you do the calculation, you get 0.0187 meter. I am giving you direct values because that's just algebra, not algebra, that is just calculation. And now we have that formula, right? Delta P by L. for a laminar flow. Where is it? Where did it go? Yeah, delta P by L, which was 32 mu U by D square. We have for laminar flow. See, this was important. If they had said it's not a laminar flow, we could not have done anything. We have this formula, 32 mu average velocity divided by d square. Okay, this is like straightforward now. And this mu is 2 to the power 10 to the power minus 5. Velocity also they have given 1. D square, then we have this 0.0187 square. So if you do these calculations, you get density was not even required, but they have given it, so it's okay. Pascal per minute. See, if you know the formula, life is so easy, right? But we should know when to use which formula, what all assumptions go into the derivation of that formula, like that. Using the formula is very easy, but where to use, that is the main thing. Anyway, what else? Do we have any other type of questions? Okay, we'll take one question again. Same thing here. Yeah, since I have not mentioned anything about power, let me just give you the formula here with the in a question only. Water is flowing in a 1 kilometer long (200 mm) dia pipe at 0.07 meter cube per second. This is your volume flow rate, average flow rate. If the friction factor is given as 0.02 and the density of water is 1000 kg per meter cube, what is the pumping power in kilowatts required to maintain this flow? I know I have not talked about power till now, but that is why I have taken this question. So till that point, before the power calculation, everything should remain same only. So what all we have? There is too much data here, so better to write that down. 1 kilometer is 1000 meter length. Dia is, and it is a rectangular pipe, so small d will be equal to capital D, which is the hydraulic diameter, 0.2 meter. Q, which is 0.07 meter cube per second. F is 0.02. Rho is 1000 kg per meter cube. These all things are given. So now, for any calculation, what do we need? FL V square by 2GD. So we don't have V, right? One thing is we can calculate V, but do we need to do that? That is the question. We can do one thing, right, which is simple. So let's say we have HF FL V square by 2GD, right? This is our standard formula. Here we don't know V, but we know Q, so we can replace V by Q, right? So same thing we did, I think, last in in The last problem also somewhere we did that. So V will be your Q by A whole square, correct? And your A is again this pi by 4D square. So I think we did that, right? Yeah, so A is your pi by 4D square. So like that. Yeah, so this becomes your formula. Okay? Because here again we put everything, right? So what you get, HF is 8 FLQ square. Maybe I should just copy it. Maybe I'll put it here. So now we have everything, right? F, L, Q, rho is not required here, but D is also there. So everything is here. So if you put these values, you should get the HF as 25.34 meter. You can do the calculations. Now what about the power? So there is a formula for that. Pumping power required. Let's say it is denoted by P. Power is P. Its formula is rho G Q HF. So you may ask me how do you get this formula, right? So see, this rho G term is again, this HF is nothing but delta P by rho G, right? So if you multiply it with the rho G, this whole thing actually is nothing but Q into delta P. Delta P, Q is your volume flow rate, and delta P is your pressure difference. Maybe I should not use P for power here because that will be confusing. I'll just leave it as it is. So power for pumping power formula is delta P into Q. You can remember it that way, or rho Q HFG. See, basically delta P is your pressure difference, right? So you have how much fluid per second you are pushing across that delta P. That is how much energy per second you are spending to maintain the flow, and energy per second is power. So that is how this formula comes. Anyway, so now just for the sake of solving the problem, you have rho G Q HF. All the values are given. Rho is 1000, G is 10, Q again given as 0.07, and HF you just calculated. So if you put all these things together, you should get 17.4 kilowatt power. So this much power pump you need to put. Yeah, so this much power pump you need to put at one end of the pipe so that it can pump 0.07 meter cube per second flow rate water up at least till 1 kilometer of the length of the pipe. Assuming it is a laminar flow. Again, this is, we have not given it. Oh, no, it's not laminar because FLV square by 2GD is the laminar turbulent, same thing. So these type of questions are typically asked. Anything else is there? See, I want to take this, series parallel connection pipe and other things like this thing, minor losses, major loss to this only, but there is something called as minor loss, right? So I want to take that in the next class, because in the next class I don't know, we don't have much to discuss only. So that's why uh, 6.10. Let me take one more question, maybe I can find some question here. Give me some time. question related to the shear stress also. Okay, we'll take this question because shear stress also is important. Okay, so there is a water is flowing through 40 mm dia and 2-meter long pipe at 3 liter per minute. What is the value of shear stress in dyne per centimeter square on the internal wall of pipe? And they have given the viscosity value as 1.02 centipoise. Okay, so here it's a I mean it's a tau problem also, shear stress problem also, but you should also remember the units of the pressure or stress and viscosity. So I'll give them here. Note, I think 1 dyne per centimeter square is 10 to the power 5 or something. No, centimeter square. No, okay. So 1 dyne per centimeter square is 10 to the power minus 1 Newton per meter square, and 1 centipoise is I think 10 to the power minus 3 SI units. What is there? 1 second, I'll just confirm. 1 centipoise. Yeah, it is 10 to the power minus 3 Pascal second. So SI units only. So let's not think about the units here. Yeah, so what all we know? Hydraulic dia is 0.04 meter, length is 2 meter, Q is 3 liter per minute. So 3 LPM I can write. Now LPM to okay, this is again. So 1 liter is 10 to the power minus 3 kg. So this is kg per minute. If I divide it by 60, it is kg per second. And if I divide it by density, it will become meter cube per second. So density is 1000 meter cube per second. Oh, no. Yeah, I mean, I just want it in liters, meter cube per second, right? So no need to multiply with density. So this is your meter cube per second. What will it be? 1 by 20. So 1 by 2, 0.5 into 10 to the power minus 4. So it will be 5 into 10 to the power minus 5 meter cube per second. Okay, I think it is correct. Maybe somebody can cross check it later. Or maybe I'll only do it. 0.003 divided by 16. Yeah, 5 into 10 to the power minus, correct. And what is the value of shear stress? So again, we have the formula for shear stress, right, at wall. So that is maximum shear stress. So that will be delta P by L into R by, oh, not R. I think it is only R. Let me just check. Where is it? Yeah, R by 2. Okay. So R by 2. Now again, delta P by L, we have this formula, right? Which we just used some time back. Yeah, this delta P by L, but this is for laminar. Now the question is, did they mention anything about laminar or anything? 1 second. They have not mentioned whether it is a laminar flow or turbulent flow, but they have not given any F value, so it should be laminar only. We can check the Reynolds number, which is rho Vd by mu. Yeah, we can do that, but I think, see, there is no mention of friction factor, right? So it should be laminar only, so we'll solve it that way only. So we know delta P by L is nothing but, I think 128, some formula is there. Na? 128 into, what is that? 1 delta P by L formula. So many formula. I am myself getting, anyway. So delta P by L, where is it? Yeah, delta P by L. 128 mu q by pi d power 4 or 32 mu VL by d square. See, we don't want V because we don't know velocity, right? We don't want to calculate it also. So better to use this 128 mu q by pi d power 4. So 128 mu q by pi d power 4, and this r by d is nothing but d by 4. Correct? No, r is d by 2, so r by 2 becomes d by 4. So here this d gets cancelled, 4 gets 3 2 into mu q divided by pi d cube. Okay. So now again this becomes a problem of putting values. What is your mu? It is 10 to the power minus 3 into 1.02. And q is 5 into 10 to the power minus 5. Pi is again 3.14 and d is 0.04 cube. Okay, so if you do the calculations, your tau wall should be uh, 1 second. It is 0.00812 Newton per meter square. Yeah, and if you convert it into the dyne per centimeter square, it will be 10 will be gone because you just multiply it by that factor. 0.0812 Newton per, no, this is not Newton, this is dyne per centimeter square. Ignore the unit change formula here because it is not the objective of this course, but that is how it is. Okay, I think we are out of the time now. If you have any questions, maybe let me just check if anybody put anything in the chat or anything. Oh, fortunately for me, nobody has put anything in the chat today.
Yeah.
Anyway, so
No, so assignment this time was easier a little bit. That's why.
it's okay. Okay, so we are already over. As I mentioned, that this other topics, which is like flow through pipe, series or parallel network, and minor losses, that type of problems. Maybe we can take them in the next class, because next class I don't think we have much new to discuss. Anyway, so let's stop here. So shall we stop? I think only Pradeep has
Yes, sir.
till
Yeah.
he is
Yes.
only the person who is bearing me.
But
Anyway,
it's difficult to remember all the formula actually. It is so there are so many actually. So
yeah,
very
yeah.
confusing.
That is the curse of this topic. If you know the formula, you have sure short answer. You will get full marks. But if you don't know, you will get nothing. So yeah,
Yes, sir.
that is the problem. Anyway, so we'll stop for today. We'll meet next
Right, sir.
Tuesday.
Yeah.
And
Right.
happy Ganesh Chaturthi to you,
Yeah,
Pradeep.
same thing to you, sir. Thank
I
you, sir.
think I should have wished in the beginning, because many people.
Not a big deal, sir. Not a big deal.
Anyway, okay. See you next time. Good night. Bye.
Thank you, sir. Thank you so much.